Hi everyone, welcome back to day 14 of Advent of Code. Today's challenge is called Restroom Redoubt. So we need to get the historians to a bathroom now, and there are multiple robots guarding the place. I don't know why the restroom needs the security. Maybe this is related to one of our visits here in some question before this. I don't think I've solved that one. So I don't remember the story, but anyway, we have to get the historians to the bathroom, and the positions and the velocities of the robots guarding it are given to us, and we have to find the positions of each of these robots after a certain number of seconds. So these are all the rules. They are telling us that for this example they have given us, they are telling us that the actual question will have a space which is 101 tiles wide and 103 tiles tall. But for this question here, we have something which is 11 tiles wide and 7 tiles tall. So this is the example given to us based on this thing. This 2 means there are 2 robots here. It took me some time to understand that. And then we have these states after how many seconds. Initially there is one robot here, which is this one, so we are isolating to that and only looking at what happens to this robot. After 1 second it moves here because its velocity is 2 minus 3. It means it'll go 2 to the right and 3 to the top, so it'll be here, which is where it is, and the initial position is 2 4, so 2 to the right, 4 to the bottom. And so after 5 seconds it reaches this spot, and the historians have to go very urgently, so they want us to find out where the robots will be after 100 seconds. And this is the state of the example input that they are giving us after 100 seconds. So after we get into this state, we have to then check how many robots are there in each quadrant, and if we have like an odd number of things, it's given to us, we already know it's odd. So if it is odd, then we don't need to include the middle lines and the robots in those lines. So in this case we have 1 in this quadrant, 2 and 3 in this quadrant, 4 in this quadrant, and 1 in this quadrant again. So we have to multiply all of that, and the safety factor we will get is our result. Okay, let's try this. Okay, so we got a solution, and so in process input we are processing the input by removing all the extra text like the p equal to and the v equal to. Then we are splitting each of the lines, and in the lines we are splitting again with this space so that we have the position on the left side and the velocity on the right, and then we are splitting it with the comma and mapping it to a number. Then this method was just to visualize to see what it looks like. I will show you once we explain everything else, but this is just making the map with dots, and wherever there is a robot it marks it as X. Yeah, here it is. So this is what it's so that I could verify by just looking at it that it's coming out right. Then find robot positions. In this, what we are doing is for each of the robot data from which we get the position and velocity, we are checking the new X after this much time where it goes, and then bringing it back to the dimensions that we are in. Since our robots, they can travel downwards, and then once they reach the bottommost, they teleport to the initial first point and then continue. So to do that, we are using modulo and getting the new X and new Y. How this works, I think I can explain it by drawing and writing down some things. But yeah, so this is what it is. The current position plus the distance they reach after this much time with this velocity, and then we bring it back to our within our area, since they can teleport. If it is negative, then we will add the dimension so that it becomes like it shows us in the positive direction, and then this becomes the new position. We push it. Then to determine safety score, we are just checking how many are there in each quadrant and pushing them to this robot counts. This robot counts I have included so that I could debug better in case something goes wrong. Finally, we multiply each of the things which are there in this robot count and send out this as the safety score, which we are getting as 12. So let's see if the same thing works for our actual input. The dimensions for the actual and the sample were different. Okay, we've gotten something. Okay, great. So now let's see what part 2 is. In the end, I'll explain the velocity part. Okay, so this one is extremely tricky, but we have to now find out what is the minimum amount of time it will take for these robots to form an Easter egg, which is a Christmas tree. This is going to be very tricky to find out. Alright, let's try coding this. Wow, okay, we're done here. We've got the Christmas tree and everything. So actually this is not how I imagined it would be. I'll explain my code first. So not much has changed in process input or visualize. And I mean, in visualize we've changed something. We've changed it from writing to console to writing it to this file. And how we got the Christmas tree, I'll tell you. Then robot positions is the same. Determine safety score is also the same as before. This new method we have added called find Christmas tree. So that takes our robot data similar to how we were finding the robot position before. Now we are just going to use the robot data and actual dimensions. Keep a track of the least safety score and then the time of that least safety score. Why least safety score? Is because suppose we take this Xmas tree my idea was that if for the least amount of safety score, if we will have a huge Christmas tree in the center, so most part of the tree will disappear because of the center part. Like if it was like this and like this, something like that, so many of them were disappearing. That was my idea behind it. It wasn't that it would be in entirely one quadrant, which also makes sense, since if everything is in one quadrant, the amount of things in the other quadrants become lower, so the overall product becomes lesser. Actually, I think I lucked out that way, because if it worked according to my logic, it would be the maximum safety score, because then it would be equally distributed among all the 4 quadrants. So I was thinking of both ways. It could either be the max or minimum. It had to be one of them, otherwise there's no way to find the Christmas tree. So I tried with minimum first to see what it's like, and so when I saw this diagram, then I was sure that okay, we've got the right answer. So I've not tried it yet, but so we will see that. So now what we're doing is we're looping through time of 0 to the maximum time, which will be the product of the dimensions, because that is the maximum number of possible movements or the period that could be possible. And then we will find the robot at each position. We'll find robot positions at each second and then determine the safety score and then check what the least was, and then we'll get that. So that's how I got the time here, and then I visualized it, saved it to that file because it was impossible to visualize on the terminal. And then I logged the time, which was 7383. So now let's see if this is right. Great. This is kind of confusing. They could have told us that this is how the tree would be or something. We had to assume it would either be the least or the max based on the previous question. Anyway, this was fun, and the picture was really nice. So also I have to explain how the velocity thing works. So suppose we have these points, and now we have to see where this, let's color it this way, where this would be after 5 seconds, and its velocity is 1, 1. So we know that this is at 0, 0, so we don't need to add the initial position. That's why this will be easy to explain. After 5 seconds, we can just say that it's moved in x-axis 5 times and y-axis 5 times, so its position will be 5. But our grid is only 3 by 3, so it will have to move 1, 2, then 3, then 4, then 5, which is this position, which in terms of the grid would be 2, 0. So what we can do to get that is this 5 modulo 3 will give us 2. That will be what is remaining here, and the same thing here, 5 modulo 3 for this one will again give us 2, so that will be here, and if you combine both the points, that becomes 2, 2 will be here. Now if you want to check that this was at 0, 0, so first second will be here, second will be here, third second will be here, fourth second will be here, again fifth second will be here. But this becomes a little different if you have an initial position. You can't just use what you get directly. So suppose your initial position is this, which is 1, 1, and you're traveling also with a velocity of 1, 1. So in that case, you will get to this position after 5. How that is 1, 2, 3, then 4, and then 5. I knew that because it will be one more than whatever it was before, but you can use this same thing again. So the velocity 1, 1, you multiply that with 5 plus the initial position 1, 1. that will give you the final one. So this will become 5 5 plus 1 1, which will give you 6 6. Then modulo 3 for both of them will look 0 0. So you end up here. But now there's one more condition in which, so now if we have this and you are here right now and your velocity is 1 minus 1, then after 5 seconds your position will be 1 and 1. So now if you add this up, this becomes 6 comma minus 4. Now if you do modulo 3 for these, it becomes 0 comma minus 1. So let's see, this minus 1 is telling us that it is going upwards, but the position minus 1 doesn't exist. So if it is less than 0 or if it is negative, you can just add the number of whatever rows or columns you are looking at to this. So this becomes 0 2. So now let's verify if this was correct. It is telling us that it would be here in the final position, but let's verify. So this goes here 1 2 3, then 4, and then 5. So that is how this velocity positioning works. Cool. So now I've explained this and we've covered our 2 parts. So see you on the next day. Bye bye.